Something truly remarkable has happened on the internet in the past 10 years, and you might not be aware of it yet. And that's that the cost of making a prediction has radically decreased. So the unit cost of trying to make an assessment of what might happen next has become so cheap that it's happening all the time, all around us on the internet, and we use it all the time. So when you ask Siri a question and she responds, what she's doing is making a prediction of what it was that you intended to say and what kind of answer you need back. When you ask what the best route to get home is through the traffic, that's a prediction about what the optimal routing and shortest time would be to get home. And so we're seeing all these new applications come to fruition based on predictive analytics. And there's a whole new technology suite out there that's helping us do that. But there's also a challenge. Even with all the computational power in the world, we're running up against limits of what's possible in the number of predictions that we can make and how fast that we can go. So my question for you today is, what would you do if you had access to all the computing power in the world to make a prediction? What's the most important prediction to you in your life? Maybe it's what might happen to your sports team this year, or something to do with your health, or even what's the best route to get home from the conference today and what to do next. And so over the next couple of minutes, I'll take you on a little bit of a journey about what predictive analytics means and how we might do this together. So prediction is all about patterns, recognizing patterns and then describing them and understanding what might happen next. And this is the simplest pattern that I could come up with that we could all do together. So it's a straight line. We can describe it using an algorithm that we learned in high school, y equals mx plus c. And we could probably all figure it out relatively quickly. And if we expanded the canvas, make a very accurate prediction about what might happen next. What happens if the pattern gets a little bit more complex? So this pattern is now starting to work in multiple dimensions. There's obviously some underlying rules, an algorithm that governs what happens here. But over time, as the patterns become less intuitive to our human brains, we need a little bit of help from computers to help us figure out what's going on behind the scenes. Then probabilities get involved. This is a pattern, it's becoming more complex again. And as the tree expands, we can see that there are some underlying rules that are governed by mathematics, but there's some probabilities that come into play every time the branch splits into two. And as humans, it's very difficult for us to figure out what might happen next with this. But if we use a computer and we design an algorithm, use some machine learning to help train that, we can get a fairly accurate prediction about which direction it might go at which time. Maybe it won't be a perfect prediction, but over time we'll get relatively accurate expectation about what happens next. But then chaos sets in. These kind of patterns are almost impossible for us as humans and almost impossible for machines to figure out as well. We could spend a lot of computational time trying to understand what the underlying rules were behind this particular chaotic pattern. We might be able to get there with a lot of computational effort and some really smart work going into it, but it's really challenging. And natural systems are more chaotic again. There's obviously some patterns underlying this behavior, but what if we add an intelligent system to that as well? So how might this shoal of fish behave over time? How do they react to each other? Which direction might they go? It's extremely challenging to work this out. And then we look at one of the most complex things that human beings do almost every day. When we drive a car, we're making predictions about what might happen next all of the time, almost intuitively. Whether that dog is going to run out from behind the bus, whether the taxi is going to turn in front of us, what color the light is going to change. We're doing this almost very naturally and intuitively as we learn how to drive. But when we build self-driving cars and put these into the same environment with us as human beings, the amount of predictive capability that those machines need to interact with us in that environment very reliably is extremely challenging. And so the amount of computational power that's needed to make those predictions and to train those machines is immense. And we're starting to run up against the limits of the computational power that supports that. One of the underlying rules that's helped us create computational power over the last 52 years is Moore's law, the doubling of computational power. And we've been riding that wave as we've created new algorithms and new computational power since then. But we're starting to reach one of the fundamental limits of how we keep up with Moore's law. And that's the size of the transistor that we can fit onto a single chip. This is one of Intel's most recent chips. The gap between those little branches on there is about 14 nanometers. Now, if you squeeze your fingers together as tight as you possibly can, the gap between your fingerprints is tens of thousands of times bigger than what's on this screen. This is getting down to the atomic limit of how small we can make something. We're almost literally counting the number of atoms to make sure that there's enough electrons to create electricity to flow across that gap and to create an electronic circuit. And so there's a real challenge right now about how do we keep up with Moore's law? How do we keep creating more and more powerful computers when we're reaching the limit of how small we can make something and therefore how many transistors we can cram onto a single chip? And so there's a number of different techniques to that, and we're seeing like multi-core computers and new technologies like field programmable gate arrays and all sorts of wonderful things. But one of the technologies that is extremely promising and potentially giving us a major breakthrough in computational power is quantum computing. So what you see on the screen here is something truly remarkable. This is developed by a team at the University of New South Wales in Sydney, Australia. The blue stuff is silicon, and the red stuff is phosphorus. And that is a single phosphorus atom that's been precisely engineered right where the team want it to be. And then some control lines next to it that can write to and read from the information that's embedded within that atom. So this is the building blocks of a quantum computer. A quantum computer says, well, what if we ignore the limit of building a transistor at the atomic level and we go inside the atom? What if we go down to the next layer of physics, into quantum physics, and start to make use of the strange behavior, the weird and wonderful world of quantum physics, and build computers that rely on that physical process as opposed to classical computers and the work around that? So this is the building blocks of some of the first quantum computers that we're going to be able to use to keep up with our predictive analytics capability. And there's teams around the world that are racing to build these right now. This is a chip that's built by Google. It was released earlier this year. This is their quantum computer. It's a slightly different approach to the one out of Australia. But this is a real quantum computer. It looks like a regular chip. It's about the size of your thumbnail. But inside there is some truly remarkable engineering to control information at the quantum level. At IBM, they've also built a quantum computer. You can use it today. You can go to ibm.com/quantum and sign up and start using this quantum computer and start programming on it. These are accessible, real machines. The shielding that you see around the computer there, that's part of a refrigeration system that cools these chips down to almost absolute zero so that we can start to play with the quantum mechanics that's going on inside. There's startup companies as well. A team at a firm called Rigetti have recently built a chip as well and are starting to make these more and more accessible to software engineers like me that are really interested in the algorithms that sit on top of that. And so we've seen an explosion in the amount of application work that's going into quantum computing over the last couple of years. This has been a field that's been highly theoretical for the last 20 years or so, but as these chips have become accessible, software engineers and computer scientists have started to look at the applications that can sit on top of that. And things like machine learning and simulation have become some of the most promising application areas of quantum computing. We're really excited about that. So let's take a look at how this is different to a classical computer. As you know, with a classical computer with a gate, it's either a 1 or a 0, on or off. There's no other possibility for that transistor to be in a state. But with a quantum computer, we can create a qubit, a quantum bit, and that's got some probability of being a 1 or a 0. And when we read that qubit, it flips into place. So we can store information within the probabilities embedded in the quantum physics. And this is extremely powerful because it allows us to encode kind of more information and more possibilities within the same number of qubits as we get in the classical computer. So let's imagine a classical computer that's got 2 transistors. That means we've got 4 possibilities to work with. It's either 0, 0, 0, 1, 1, 0, or 1, 1. And if we wanted to find the right answer to what might happen next with the prediction, we would have to step through each possible one at a time, each possible state, and see if that was the correct answer for us. But with a quantum computer, we can reorganize this into 2 qubits and store 4 possible states within there with some probability that we can measure simultaneously. So it's got all of these states existing at the same time with a probability that we'll pull something out of it. So rather than stepping through them one at a time, we can keep all of this information stored there, measure once, and get the right answer from that that we can then use to make our prediction. And this is where I'm going to start to blow your mind. We can start to play with the probabilities of this and entangle multiple qubits together. And while it's computing, play with the probabilities so that we can get the right answer for us out of that. So let's say, for example, that we always wanted the two qubits to work in opposite directions. So then we take the probabilities from being 25% for each possible state and change that to being 50% for two states there. So while our computational work is going on, we're playing with the probabilities inside the system and helping us find the right answer out of that. What's truly remarkable about this is that we only need a small number of qubits to store a lot more potential information than in a classical computer. And so with just 30 qubits, we could potentially run faster than the fastest supercomputer that exists in the world today. With 300 qubits, that is more computational power than all of the computers that exist on the planet today in one computer. And we're at the really early stages of building these machines. We've got a long way to go, but it's incredibly exciting to do this. And so what can we do with a quantum computer? It will transform the way that we do predictive analytics. And I don't think you'll access one in your pocket. There won't be one in your cell phone. But within a cloud platform, there'll be multiple quantum computers, multiple different types of computers running alongside each other. So you'll be accessing CPUs, graphical processing units, all sorts of different machines. And a quantum computer is a special case that runs alongside those and allows us to work with probabilities to solve some hard problems. The ones that we're particularly interested in the very early days of quantum computing are machine learning, helping us do predictive work, large-scale optimization problems like traffic routing, and quantum chemistry, understanding how molecules work together, how cells behave down at that level, and it's all about prediction. And so we can't do this alone. There's a whole new workforce that we need, a whole new skill set that's required to build these applications. We need to combine things like software engineering and quantum algorithm research, data analytics into quantum software engineering, and then create a skilled workforce around quantum data analytics to make use of these remarkable new machines. And that's where I invite you all to come on this journey with us. We're at the beginning of a new revolution in the way that computers are built. It's opening up a remarkable new set of applications that were previously intractable to us, that we couldn't solve even with all the computing power in the world today. And so what we're doing at my company is helping to train people to do that work. We're running hackathons around the world. We're running training sessions to take software engineers and computer scientists and data scientists that haven't worked with quantum computers before and to teach them the fundamentals of how these new computers work, the kind of algorithms that we can run on top of them, and open their mind to the potential of the applications that we can run with these new computers. What we're seeing is that despite all the theory that we've had over the past 20 years or so about what's possible with a quantum computer, that there's, as we put tools into the hands of people and they start to explore this for the first time, their imagination starts to run wild about what they could potentially do with an ability to play with probabilities and an ability to play with the potential of quantum computing. And so we're incredibly excited about where these computers might take us. We're at the very beginning of this journey, but we've got the potential to open up a whole new level of computational power and do some remarkable things with it.